NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will find where two quadratic functions intersect by following three clear steps. Define the functions, set them equal, and rearrange to a single quadratic equation. Step 1. Write the two functions in standard form. We will use a sub 1, b sub 1, and c sub 1 for the first parabola, and a sub 2, b sub 2, and c sub 2 for the second. Now, to build intuition, we will also sketch two example parabolas on a coordinate plane. Step 2. At intersection points, the y values match. That is the intersection principle. Y sub 1 equals y sub 2. So we set the right sides equal. A sub 1x squared plus b sub 1x plus c sub 1 equals a sub 2x squared plus b sub 2x plus c sub 2. On our diagram, those matching y values occur where the two curves cross. Step 3. Move all terms to one side and combine like terms. This gives parentheses, and combine like terms. This gives parentheses, a sub 1 minus a sub 2 parentheses x squared, plus parentheses b sub 1 minus b sub 2 parentheses x, plus parentheses c sub 1 minus c sub 2 parentheses equals 0. This is a quadratic equation in x, so it has at most two real solutions. Therefore, two parabolas can intersect at most twice. Our goal is to find the equation of the straight line that passes through the intersection points of two parabolas. We'll do it elegantly using elimination of the quadratic term. Here are the two functions. Equation 1, y equals x squared minus 3x. Equation 2, y equals negative 2x squared plus 4x plus 3. We want the line through their intersections. Step 1. Points of intersection satisfy both equations. So set the right sides equal. X squared minus 3x equals negative 2x squared plus 4x plus 3. Move everything to one side to get a standard quadratic in x. The discriminant is b squared minus 4ac, which is 49 plus 36 equals 85. So there are two distinct intersection points. Step 2. To get the line through both intersection points, take a linear combination that eliminates the x squared terms. Multiply equation 1 by 2 and add to equation 2. 2y equals 2x squared minus 6x. Add to y equals negative 2x squared plus 4x plus 3. The x squared terms cancel to give 3, y equals negative 2x plus 3. Solve for y. Divide both sides by 3 to get y equals negative 2/3 x plus 1. This is the equation of the chord line through both intersection points. Now let us visualize. We will graph both parabolas and the line. Then we will mark the two intersection points and show that they lie on this line as expected. In this lesson, we will prove a beautiful fact about quadratics and the mean value theorem. For any quadratic function of the form f of x equals ax squared plus bx plus c, the mean value theorem point, the lambda inside the interval, is exactly the midpoint between alpha and beta. That is, lambda equals open parenthesis alpha plus beta close parenthesis over 2. Let's first build geometric intuition. We will draw a quadratic curve and an interval from alpha to beta. The mean value theorem guarantees there is a point lambda where the tangent slope equals the secant slope across the interval. For quadratics, we will see visually that this lambda sits exactly at the midpoint of alpha and beta. We start with axes. Now, here is a sample quadratic. We mark alpha on the left and beta on the right. Connect the 2 points with a secant line. Find the midpoint, that is alpha plus beta over 2. Draw the tangent line at this midpoint. Notice how the two slopes match exactly. Now let's prove this algebraically for any quadratic. The mean value theorem says there exists a lambda in the open interval such that f prime of lambda equals the difference quotient f of beta minus f of alpha over beta minus alpha. For a quadratic f of x equals ax squared plus bx plus c, we have f prime of x equals 2ax plus b. Plugging x equals lambda into the mean value theorem equation gives 2a lambda plus b equals the fraction f of beta minus f of alpha over beta minus alpha. Notice the constants c cancel. Factor a and b in the numerator, and apply the difference of squares identity. Beta squared minus alpha squared equals open parenthesis beta minus alpha close parenthesis times open parenthesis beta plus alpha close parenthesis. Then the beta minus alpha terms cancel in numerator and denominator, yielding 2a lambda plus b equals a times open parenthesis beta plus alpha close parenthesis plus b. Now subtract b from both sides and divide by 2a. We get lambda equals open parenthesis alpha plus beta close parenthesis over 2. This shows the mean value theorem point for every quadratic is exactly the midpoint of the interval. Let equals open parenthesis alpha plus beta close parenthesis over 2. In this lesson, we will visualize tangents to a quadratic function and show two core rules. 1. A point on the parabola admits exactly one tangent. 2. A point outside the parabola admits exactly two tangents. We start with a clean diagram and an example setup. Let's draw axes and the parabola y equals x squared. We'll use this as our shared diagram throughout. Step 1. A point on the curve admits exactly one tangent. We pick an on-curve point at x equals 1.2. We draw the unique tangent line using the derivative. The derivative of y equals x squared is 2x, so the tangent at x naught is y equals 2x naught times x minus x naught plus x naught squared. Any other line through the same point will intersect the curve at 2 points, not 1, which breaks tangency. Step 2. A point outside the parabola admits exactly two tangents. For an upward opening parabola, the outside non-convex region is below the curve. We choose the point 0, -2. There are exactly two tangent lines through this point. Algebraically, any line through that point has y equals mx minus 2. Tangency with y equals x squared needs a discriminant of 0 for the quadratic x squared minus mx plus 2 equals 0. That yields m squared minus 8 equals 0, so slopes are plus or minus 2 root 2. Equivalently, parameterizing tangents to y equals x squared as y equals 2tx minus t squared, passing through 0, -2, gives t squared equals 2 and t equals plus or minus root 2. Those are the touch points at x equals plus or minus root 2. For contrast, a point inside the convex region above the curve admits no tangents to this upward parabola. For example, the point 0, 2 lies above every tangent line of y equals x squared, whose y-intercepts are non-positive. To summarize, 1. Any point on the quadratic gives exactly one tangent via the derivative. 2. Any point outside in the non-convex region gives exactly two tangents, verified by a discriminant of 0 or by the two parameter values of the tangent family. We will build an intuitive visual method to decide where a point sits relative to the graph of a quadratic function. Our function is f of x equals ax squared plus bx plus c, and we will test a point m with coordinates alpha, beta. The core idea is to compare beta, the y-coordinate of the point, with f of alpha, the y value of the parabola at the same x position. Let's see both concavities side by side. On the left, the parabola opens up, so is positive. On the right, it opens down, so is negative. We will use the same alpha and compare beta to f of alpha in each case. First, for a greater than 0, if beta is greater than f of alpha, the point is above the curve, we call that inside the bowl. If beta is less than f of alpha, the point is below the curve, we call that outside the bowl. If beta equals f of alpha, the point lies exactly on the graph. If it is greater than 0, then beta greater than f of alpha means inside. Beta less than f of alpha means outside, and beta equals f of alpha means on the graph. If it is less than 0, the comparisons reverse for inside and outside, while equality still means on the graph. This gives a fast, reliable test. Compute f of alpha and compare it to beta. In this lesson, we'll find the shortest distance between a parabola and a line and build geometric intuition along the way. Here is the example. Y equals x squared plus 4x, and the line y equals 2x minus 6. Let's draw both graphs on the same axis. We'll plot the parabola y equals x squared plus 4x, and the line y equals 2x minus 6. Our goal is the shortest distance between the curve and the line. Geometrically, that shortest path will be perpendicular to the line at the closest point. First, check if the line intersects the parabola. Set x squared plus 4x equal to 2x minus 6. This becomes x squared plus 2x plus 6 equals 0. The discriminant is 2 squared minus 4 times 1 times 6, which is negative 20. A negative discriminant means there are no real intersection points. So the line and parabola never meet. The closest point on the parabola occurs where its tangent is parallel to the line, so set the derivative equal to 2. 4, y equals x squared plus 4x. The derivative is 2x plus 4. Solve 2x plus 4 equals 2. We get x equals negative 1. Plug back into the parabola, y equals negative 3. So the candidate closest point is m of negative 1 comma negative 3. The tangent at m must have slope 2 as well. Its equation through m is y equals 2x minus 1. We'll sketch that tangent to reinforce the idea of parallel directions at the closest point. The shortest path to the line is along the perpendicular from m to the line. The line in standard form is 2x minus y minus 6 equals 0. The distance from a point x naught, y naught to a x plus b, y plus c equals 0 is absolute value of a x naught plus b y naught plus c, divided by square root of a squared plus b squared. For m of negative 1, negative 3, and a equals 2, b equals negative 1, c equals negative 6, we get absolute value of negative 5 over square root of 5, which simplifies to the square root of 5. So the shortest distance is the square root of 5. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.